Hello, and welcome to another lecture in the course. So today we'll talk about the maximum modulus principle, which is subsection 3.3.3 in the book. All right. So this is a very useful, simple consequence of Cauchy's integral formula, and actually just the Cauchy's integral formula in the circle that we did. We don't even need a very complicated Cauchy's integral formula for this, and it's incredibly powerful, actually. Much more than what it looks like. All right. So what is it? What is the maximum modulus principle? It's basically something that allows you to get estimates. So there's a couple of versions of this. It all has to do with inequalities. So the most basic versions of this is basically where the name comes from, and it's basically says, keep repeating the word basically, it says that holomorphic functions do not have local, the modules of holomorphic functions does not have a local maximum, right? Or cannot have a local maximum unless it is constant, right? So if I have a domain and a holomorphic function, and the modulus of this holomorphic function achieves a local maximum somewhere on U, anywhere on U, then f is actually constant, right? So it's the modulus is always kind of a saddle surface. So holomorphic functions, you can think of them as being sort of always kind of saddle surfaces. They, if they grow in some direction, they go down in other directions, and vice versa. That's basically what holomorphic functions are. We're gonna look at there's a corresponding minimum principle, but that's a little bit more complicated. I'll talk about it later. We have to allow zeros, right? So you can clearly have, like, for example, the function z has a minimum, and the modulus of z, right, has a minimum at the origin. So that's allowed. It's not constant, but it's actually the only thing that has the only kind of minimum that you're allowed. So it's usually stated for a maximum, because then it's then you don't have to worry about the zeros. But it's fairly simple to state the minimum modulus principle, as well as, like, if you take care of the zeros, it's the same idea, except you have to worry about what happens at zeros. So all right, so let's think about the maximum principle, right? Basically, it says that if you have an inequality somewhere, even just locally, you have some inequality, the one that gives you a local maximum, then you actually have an equality, right? Which is a lot stronger, a lot stronger statement, of course. So what is the basic idea? There goes the word again, basic. It must be a basic kind of day. What's the basic idea of this proof? So the idea is that Cauchy's integral formula really says that one of the things that it says is that at the center of a disk, the function is actually the average of its values on a circle, right? So if you think about that, how could an average of values be bigger, right? I mean, the average is going to be somewhere in the middle of the values, right? So it can't be bigger than all of them, right? That's basically the idea. All right, so let's suppose we're supposed to prove this, right? So let's suppose that the modulus achieves a local maximum at some point p, And without loss of generality, let's just assume that p is 0, just so that we don't have to keep writing it. It's easier if it's just equals 0. It's gonna make some of the formulas simpler. All right. Now, the other thing is that we could multiply by some unimodulus constant, by some e to the I theta, to assume that f at 0, which remember that's what our point P where we're having a local maximum is. Let's suppose that f at 0 is actually positive, right? Or at least non-negative, right? I mean, it could be 0, but then you would be already 0, all labor would be essentially be done. But let's just, suppose it's non-negative, right? Which we can always do, right? I mean, it has some argument, and we just multiply by e to the I theta to get rid of that argument, right? And so we write that like this. We say f of 0 is bigger than or equal to 0, even though it doesn't really make sense, right? Because f at 0 is a complex number, and the bigger than or equal to is something about real numbers. But when we write that, we mean f at 0 is a real number, and it is non-negative. All right. So now take a closed disk, delta sub r around 0, that still lies in U. So we want it to be small enough so that actually the whole closed disk, so including the circle, lies in U, right? And since this this function achieves a local maximum at the origin, we can also assume that R is small enough so that whenever Z is in this closed disk, that we have that f of Z is less than or equal to the modulus of f at 0, which is just equal to f at 0. We just said that it's non-negative, right? So yeah, we can always choose a small enough positive R that does this. All right. So now let's apply Cauchy's formula. We said, this is all because of Cauchy's formula. So let's apply Cauchy's formula. I was actually going to apply it a couple of times. So f at 0 is equal to modulus of f at 0. That's just what we made it. And f at 0, well, this is what Cauchy's formula says. We have this disk inside U, right? So yeah, that's what Cauchy's formula says. That integral is equal to f of 0, right? Now let's actually compute what that is. I mean, that is rather simple to compute, right? I mean, we can, the Z travels around this disk of radius r around the origin, so we just parameterize it as r e to the it. Then dz would be this guy over here, right? We get an I coming out, but yeah, doesn't really matter here. And yeah, and we're putting an f of z over here, right? So that's definition of what this integral is. All right, so now we estimate this integral by the simplest possible estimate. We just bring the absolute value inside, right? If you bring the absolute value inside, I mean, there's a couple of things that just cancel out immediately. You could cancel out the I if you wanted to. It's just going to get killed by the absolute value anyway. Then r e to the it cancels out this r e to the it. The e to the it cancels out, and it's going to get killed by the absolute value anyway, but it cancels out, so it doesn't really matter. So 2 pi, absolute value of 2 pi is still 2 pi. So when I bring that inside, I just get the modulus of f, right? Now, if you look at this is precisely this this guy over here, if you remember from Calc 1, I know that we're teaching this in Calc 1, this is the formula for the average value of the modulus of f, right? Over this this range of t, right? All right, now we know that f was actually f had a local maximum at 0, right? And it was the value at 0 was bigger than any value in this whole closed disk, including on the boundary. So we know that whatever's inside is bounded from above by f at 0, right? That is positive, whatever that value is, right? And now, if you look at this, right? I mean, there's no t inside that integral, right? We're just integrating a constant and then over the interval 0 to 2 pi, and then we're dividing by 2 pi, right? So we just get that constant out front, right? Now, notice that we have f at 0 here and f at 0 here, and then we have a chain of inequalities. What does that mean? It means that these inequalities weren't really inequalities at all. They had to be equalities, right? That's the only way that that could possibly work. So we actually get equalities. So all of this are equalities. All right, now we have this inequality, which was really just saying that f at 0 was a maximum, a local maximum, right? So this is true for all t, right? So if we now we look at these two intervals, and they are equal, right? And so if we subtract them, right, we subtract this from this, right, we get this formula over here. And furthermore, what's inside is non-negative, right? So if you want to show that something is 0, if you just show that the interval of that is 0, well, that's not good enough. But if you show that something that is non-negative has 0 integral, yeah, then that thing is 0, right? I mean, you need something maybe a little bit more. We have continuity here, right? I mean, this whatever's inside is continuous, right? So that's why we get for all t. If you're also taking real analysis, right? You go, oh well, you know, don't we get just for almost every t? Yeah, but what we have is continuous, so we get for all t, right? So we get that what's inside is 0. So we get this formula over here for all t. And if you think about it, we got it for all small enough r, right? Because the same thing worked for every small enough r. Now, it's not quite finished, right? We're kind of maybe like the main part of it is maybe finished, right? There's actually a couple of ways to proceed now. What we proved is that in a neighborhood of 0, the modulus of f is constant. And so you can prove that if the modulus of f is constant, then the function is constant. There's an easy way to prove that, for example, using the Cauchy-Riemann equations. But since we have this set up with the with all these intervals, maybe we can just keep doing the same thing and get another. I mean, all of these ways are going to be approximately equally difficult, right? But basically, we have to show that it's not just that the modulus is constant; it's just the function itself is constant. All right, so let's apply Cauchy's formula again. So we have if we take that this integral over here equals f of 0. That's what we have over here, right? Well, now apply Cauchy's formula to get that equals this guy over here, right? That's just what f of 0 is by Cauchy's formula, right? We essentially did that over here, when we applied, went from here to here and then canceled out, right? You'd get this sucker over here. So, right, so now we have that these two integrals are, right, this integral is equal to this integral. Well, that means that we could subtract them, just like maybe we did over here, sort of a similar idea, except now we're subtracting, slightly different integrals, right? We are, we have the modulus, so forget about the real part so far. We have the modulus of f minus f, right? So that's the integral that we're doing over here. We know that is 0, right? Now, if that is 0, the real part of that is 0. Right? So that's why we're taking the real part over here. I mean, why not? Right? I mean, that's a weaker statement, right? We might as well make it. So therefore, we have that's equal 0, and the real part, well, that can go inside. I mean, how do you compute the real part of an integral? You compute the integral of the real part of the inside, and well, the inside, the only bit that has possibly an imaginary part is the second part over here. So that's why the real part just lands out here, right? So we have that this integral out here is 0, right? So now it's an integral of a real valued function, and it's 0, and we're going to play the same game as over here. It's also continuous. Furthermore, if I take the modulus of any complex number and I subtract its real part, that is always non-negative. That's a fairly simple just geometry, right? So it's right. I'll let you think about it. Draw the picture, and you'll see why that's obvious. So you have that the modulus of a complex number minus its real part, that's always non-negative. That's precisely what we have over here, right? We have the modulus of a complex number minus its real part, right? We're integrating that. So what we have inside is non-negative. Again, it's non-negative continuous function, right? That's what we're saying here. And therefore, this integral being 0 means that the modulus of f is equal to the real part of f for all t. But that also means that the imaginary part of f has to be identically 0. There's no way that you're gonna get, if the real part is already equal to the modulus. If you think about how do you compute the modulus, right? The real part squared plus the imaginary part squared, square root of that. Well, I mean, if the real part is already as large as the modulus, the imaginary part had better be 0. Well, that means that you have, well, first, f is equal to its real part, right? Because the imaginary part is 0, right? So f is equal to its real part, which is equal to its modulus, which is equal to f of 0. That's what we proved before. This was for all t, right? So now we have not just that modulus of f is equal to the some constant. It's f, right? And this was, I mean, so far in some sense we've only did it on one circle, but this entire argument worked for every small enough r, right? And so since it's true for all small enough r, that means that we have that this guy is equal to this guy, right, on a whole disk, right, on a whole small enough disk. So that means that the set where f is equal to its constant contains an open set. F is defined in a domain, connected open set, and therefore f is constant by the identity term, right? Once you have that it's constant in a small neighborhood, it's constant everywhere, and we're done, right? So that was the first version of the maximum modulus principle. Maybe it's sort of the simplest one to state, and the simplest one to prove. There's a couple of other ways of stating it. For example, one of them is the following, and that's actually one that gets used quite a bit, but it's maybe a little bit more complicated to state. But that's the one where you see how inequalities come up. Maybe it gives you more of this of how to use the maximum modulus principle. So suppose that you have again a non-empty open set, but now bounded, right? So bounded open set. So in particular, the closure of U is compact, right? And let's suppose that we have a function defined on the entire closure of U. And this function is continuous. So what does that imply? It implies that f achieves a maximum on U closure, right? Because we have a continuous function, or the modulus achieves a maximum on U closure, because we have a continuous function on a compact set, right? All right. So now, if we also assume that the restriction to the interior is holomorphic, right? So we have a continuous function up to the boundary, inside it's holomorphic, then the conclusion is that that the modulus of f achieves a maximum on the boundary. So we already know that it achieves a maximum somewhere on the closure, right? On U bar. But we're saying it's not just on U bar. It cannot be inside. It has to be on the boundary, right? They can probably sort of, quickly figure out how that follows from the first version of the maximum modulus principle that we gave, right? Now, in other words, this is really the inequality that we're getting, right? This is sort of the useful thing that gets used a lot. That's the inequality that we get out of the maximum modulus principle. Is that in such a setup, and a lot of times the way this works is that when you have a holomorphic function defined on some larger set, and you choose a smaller, this U would be some sort of a subset, right? So that you have that f is still continuous on the closure of this set. So so under that setup, what you have is that the supremum of the modulus of f inside, it doesn't really matter if you take z in U or z in U bar because of continuity. It's going to be the same thing. So if we have the supremum of f inside is bounded by the supremum of the modulus of f on the boundary, right? So we have we're basically bounding bounding the modulus on a very large set on the inside by knowing its maximum on a very small set. Right? So that's really where this is where this is really becoming useful, right? We get some sort of an inequality, right? Analysis is all about inequalities, getting inequalities. Well, here's one, right? We get something, a function over a lot of points bounded by that same function over fewer points, right? It's easier to figure out, hopefully, what the right-hand side is than what the left-hand side is, all right? A lot of times, the way this works is that, on the boundary, you stay away from something bad, right? All right. So, prove an exercise, right? It's not too hard to prove from the first version. Now, as I said before, there's also maybe a third version, which would be a minimum modulus principle, and it's essentially the same sort of idea, except you have to avoid zeros. So you can, again, suppose that you have a domain and a holomorphic function on this domain, and suppose that f achieves a local minimum at some point p. Now, it could happen that fp is 0, in which case that doesn't really say anything, right? That clearly can happen. But if f of p is not 0 at this local minimum, then f is constant, right? So for example, if f has no zeros, then f cannot achieve, the absolute modulus of f cannot achieve local minimum, right? If it has zeros, yeah, clearly it can achieve those zeros. All right, so that's the maximum modulus principle. So next time, what we're gonna do is so we really have sort of enough machinery to pop out a bunch of very interesting theorems, including the fundamental theorem of algebra, right? So it's just going to be, we're going to prove Cauchy's estimates, and Cauchy's estimates are going to give us Liouville's theorem, and Liouville's theorem is going to give us fundamental theorem of calculus, algebra, sorry, not calculus, and it's just going to pop out like one after the other. They're really, really simple. So that's what we're gonna do next time. So see you then.